I like to talk about 1 billion browsers and that sort of thing. Microsoft Edge just released their Get User Media support, so I expect that to be a very exciting thing. Microsoft is very heavily invested in WebRTC, and I expect them to make very quick progress catching up to where we are on where Chrome and Firefox are. I mentioned like some of the other apps that are using WebRTC. If you add up all the downloads, just counting like Play Store figures, we get to over 3 billion downloads. That's pretty awesome. There's a blogger, Sahi, who keeps a database of WebRTC companies, over 600 startups built around WebRTC. Like, I'm creating jobs, like you are creating jobs. This is an awesome thing. And just great uptake on like our videos and all of our developer materials. People are actually spending a lot of time consuming the content that is being produced. So anyway, that's where we are now, taking a look backwards. This is kind of like the basic, sort of idea we had around WebRTC. We kind of got it up and working pretty quickly, in the first 2 years. We had it running in Chrome within 2 years of starting the project. And so sometimes people ask me like, "Oh, what do you guys work on now?" As if like, we finished that WebRTC thing, and then like we kind of went and decided to go to the beach and just rest after all our labor. And well, I wish that were true. For a variety of reasons, anybody who's spending time with this knows that like WebRTC apps are super fiddly. Just like the real-time nature of things, you have to work across all different types of devices, all sorts of operating systems, all sorts of networks, and like if you have anything like where frames are delivered late, the eye sees that immediately. Like if anything goes wrong, if anything is not perfect, it just doesn't work. And it's like encryption. Like if you don't do every single step right, you wasted your time. So that's a kind of a high bar, and it's very challenging. And one of the things that's super challenging about it is that for a long time, we had Chrome as our primary target. And we got things working pretty well in Chrome, and we thought, hey, let's make sure things work on Android and iOS well. And to be frank, we sort of treated it as like, all right, well, we'll sort of port our stuff to Android and iOS, and then we'll see it works, and we'll consider it, hey, we work on Android and iOS. Well, it turns out it's almost really a totally different ballgame on Android and iOS. The devices are crappier, they have less processing power, the networks are different, like everything is different, it's a different ballgame, and even the application lifetime model is different. Every time the app, you hit the lock button on the phone, the app is being killed, pushed to the background, any network connections are severed, and you have to think about things like in almost a totally different way. You think about signaling in a different way. And when we finally internalized that, we realized there's a ton of stuff we need to do to make WebRTC awesome on mobile. So we had this sort of realization, 2 years ago or whatever. And so over the past 2 years, we've been spending a ton of time, making stuff better, specifically on mobile. And so I won't go into all the details of this because I only have 15 minutes, but there's a lot of stuff in here, and there's a lot of stuff we've been making better, especially on the iOS and Android side of things. And my other pet peeves, people talk about WebRTC, and it's like, oh yeah, so that's like the codecs, right? It's like, H.264 or whatever. I think there's a lot more in codecs in this picture. Anyway, so this is one of my favorite examples. One of the things we realized about a year ago is that a lot of times it took forever, like literally forever, like it would never happen, for when you started a call, for you to get up to HD bit rates. Many of you who have worked with the WebRTC stack know that when we start off a video call, we start the video at a low bit rate, and then we kind of gradually build over time to get to a high bit rate. And this is the same thing that TCP does as it kind of establishes its window and how fast it can actually be sending data. But one of the things that we found out was that sometimes we would never ramp up. And that's because the algorithm that we use to actually determine how much bandwidth is available is all based on delay. When it tries to figure out, am I sending too much data, it's looking for a signal from internet routers that their queues are starting to fill, and as a result, they're backing up packets, and they're being delivered slightly later than you would expect to the destination. And so you have this very kind of weak signal that, hey, packets are being delayed just a tiny bit, not dropped, just delayed a tiny bit, and that means you're sending too much, and you need to start backing off, or else WebRTC is going, or else the routers are going to start throwing away your data. Well, it turns out with Wi-Fi, you can end up in this sort of thing where you're sharing a spectrum, and Wi-Fi is going to basically batch up your packets depending on whether you can get a time slot for your packets. And the way that Wi-Fi time slots your packets can cause you to basically have some of your packets being delayed, not due to router queue filling, but due to the fact that this time slotting is occurring. And so our algorithm, the old dumb algorithm, was like, oh, hey, we see delay, we better back off. But in cases where you have like a ton of people competing for the same Wi-Fi access point, this time slotting is happening all the time. And so we were always seeing this delay kicking in from this time slotting, and we're saying, hey, we're sending too much data, we need to back off. And as a result, you would never get to HD quality. And so we spent a bunch of time sort of like trying to figure out like this. We basically looked into what's actually happening on the network, trying to understand the problem. We actually found out it was Wi-Fi time slotting. And so on the left is sort of what the old behavior was. We'd start ramping up, and then we'd hit like some sort of ceiling, and then we'd sort of drop off and never recover. And here you see on the right, we get up much, much faster, and then we would stay pretty much at network capacity almost the entire time. Since then, we've gone further, and like, if I see this number, my team would show me this, and I'd say like, well, this is pretty good, but like, we don't get the HD for like 30 seconds. Like, what's up with that? We now have this kind of initial probing thing, where in the initial keyframe that we send, we sort of put the packets on the wire in a way where we can kind of start seeing that initial delay from the very first frame we send. And based on that, we can often get to HD in 1 or 2 seconds. In fact, I think on Mac Chrome, we now get to HD in like 50% of all cases within 1 second. Yeah, so this is, I forgot I actually had the slide for this. The blue is the old line, and the brown is the new line. And so I think everyone can kind of agree that getting to HD after 45 seconds is not as good as getting to HD in 1 second. All right, so we talk about codecs a lot. People ask me about H.264. We're going to support H.264. Our goal is to get it in Chrome 45. A lot of people have been asking for it. We've looked actually pretty deeply into this. The Cisco open H.264 stuff is what we're going to use. We've also sort of, looking under the covers, found that that's not as good as we would have hoped. But it's there, and if you need to use H.264, we'll support it. But we're very excited about VP9. VP9 sort of exists in experimental mode right now in Chrome, and we expect that to go from experimental mode to kind of on by default within the next month or two. And the great thing about VP9 is basically for 15% more compute, you get 40% fewer bits, or 40% better quality at the same bits. And so, we didn't try this out in Webrtc first. Pretty much over half the videos that are being streamed on VP9 or on YouTube right now are being encoded using VP9 because of that same thing. And the same quality, you get 40% fewer bits. And we're seeing right now, like, the hardware is like a big deal. We're trying to make sure we get good hardware support. We have good hardware support now in Android for VP8. We're making sure we get support the hardware on iOS for H.264, and we're working to get VP9 to chips. And they'll be VP9 devices will be showing up in 2016. This is just something to be thinking about. The main thing is that the VP9 patent situation is pretty awful. Or sorry, VP9 patent situation is great. The HEVC patent situation is awful. We think VP9 will be a great solution to this problem of giving people like a royalty-free way to get next generation compression without just awful licensing restrictions. So do a little demo here. I like to talk about VP8. I like to talk about hardware acceleration. We've done a lot of work to support hardware acceleration. So do a little demo. This is a demo we did at I/O today. I got this Nexus 6 device here. All right, so we got this Nexus 6 device here. And we call into this app RTC room. You may be seen this app once or twice before. Whoops. All right, so here we have this device here streaming, and this is using the hardware encoder built into the device. And you can see we're getting a nice HD 720p stream coming off of like this mobile device, and it's all using the hardware codec. And like, the quality of this is like really, to even get this on desktop like a year or two ago would have been like really difficult, and we're now getting this in a device that you can get, fits in your hand. And you know, I think it makes for a really good thing. You kind of just walk around the room, and you can see not just like the quality of what we're like sending is really great, but also you know, quality of what we're receiving. You know, the screen here, you know, everything just looks fantastic. And so like this is kind of what I talked about when I said we need to make sure WebRTC just works fantastically on mobile. And it's not just porting desktop, it's making sure that you actually take advantage of all the features that are present on these devices. So, you know, on Android, we've got the Media Codec API. On iOS, there's Video Toolbox, which we're working on and fully integrating. And like when it all sort of works together, like here I am using your guest Wi-Fi, and I'm able to stream this like 720p video, which just looks fantastic. I mean, it makes for just a fantastic experience. And like I've used the word fantastic a lot, but I think this is really fantastic. You guys make me look good, right? Yeah, it's always the case. All right, so I may have blown through my well, oops, I may have blown through my 15 minutes already, but let me just sort of get ahead to what's coming next. So we've been doing a ton of work, as I said, around mobile, and one of the things that really is critical, I think, is just like making all the everything related to performance fantastic. And that includes like the quality of the video that's sent, includes how fast it is to actually set up a call, includes how much CPU do we spend, because like energy, these devices have improved massively in terms of battery life over the past couple of years. And a lot of that is just because like the system now is like the screens are more efficient, the network is more efficient. We need to make sure the apps are efficient. And so this is a bunch of stuff the team has been working on, over the past 3 to 6 months. And in WebRTC, we've kind of rewritten the signaling from scratch to basically be like super fast for setting up connections. We use WebSockets. We do a bunch of caching things. I talked about this at I/O a little bit. I won't get into full details, but basically, like we think that for WebRTC, 500 milliseconds is our typical time for setting up a call. And that's what people really should be shooting for. That like our goal is really that from the time you hit join or the time you hit answer to the time you have full audio and video going should be half a second. And same thing for getting up to HD, getting up to full quality call. Again, we should be talking about like hundreds of milliseconds, not seconds or tens of seconds. Another thing that this is probably only of interest to like crypto geeks and everything, but like one of the things that's super slow, like end-to-end encryption is awesome. We love end-to-end encryption for so many reasons, not least of which is that we don't even have the keys. If someone comes to us and says, hey, hand over your stuff, it's like, well, that's great, but I don't even have like, the keys for this, good luck. So we love end-to-end encryption, but one of the issues is that actually generating a certificate, we've actually seen on mobile devices it can take you 5 seconds just to generate a 1024-bit RSA key. And so like 5 seconds is kind of a long time. And if you want to have like different keys for each call so that you don't have like any sort of linkability of calls, like that's a lot of time you're just spending like warming up the device. So what do we do? Well, there's this thing called elliptic curve encryption, and it happens to like have basically all upsides and no downsides. This is probably the easiest way to describe it. You get the same security, and it's much faster, and also like the number of bits required to like do signatures and everything also much smaller. So we're switching basically everything else to support ECDSA certificates, and basically if you're making an application that sort of has any assumptions about RSA, it would be good to start thinking about, well, can my app work with ECDSA? So this is going to happen in Chrome soon. We're going to support ECDSA sort of side by side with RSA, but eventually like, everybody should be moving to ECDSA. It's way better. You still get end-to-end encryption, and you don't pay for it. It's awesome. Hardware and code. I just showed you the hardware and code on Android. It works fantastically well now. The specs on some of these new phones that are coming out will just blow you away. 1080p encode at 120 FPS. The hardware encoder is capable of. The cameras are getting really, really good. The new S6 camera, fantastic. The experiences you can now do in these mobile devices, they're actually better than what you get from most desktop webcams. It's really phenomenal. I mean, like even this, like you can do way better now on mobile. I never thought I would say that. And lastly, Echo. People are always coming to us and saying, hey, like I got Echo on this machine or blah, 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 all these things, and especially on Android. Now, on some platforms like iOS, you have a hardware echo canceller. On Android, we often have a hardware echo canceller, but not always. In those cases, we still need to make sure like speakerphone mode works okay. And so we have this new thing. The main issue with Android is that whenever you're doing echo cancellation, the hard part is knowing when the output signal goes out, how long does it take for that to be picked up by the microphone again? And so sometimes the operating system says, hey, here's how long the delays are on the output side, here's how long the delays are on the input side, you can calculate it, you can find the signal very easily. On Android, you don't have anything like that. So we have to basically find it algorithmically. And that's what we call DAAEC is, delay agnostic audio echo canceller, acoustic echo canceller. And so what it does is sort of uses some magic processing to find that input signal or output signal and the output signal, lock on to that timing and cancel it. And so the short story is, no matter what device you're on, we think with this, we're going to give you a great echo cancellation. Basically, we're going to cancel any echo that's there. Last thing is just around mobile networks. We want to make sure that we work on 3G networks, 4G, 2G. But we also want to make sure that the case is very, very common. You're on a call, you're on Wi-Fi, you go out the door, now you're on 3G. Like right now, it's not a great experience. You either have two options. One is burn a lot of energy by keeping both the Wi-Fi and the 3G radio on, or wait for the call to drop on Wi-Fi and then switch over to 3G and have several seconds of dead air. We think we can do this way better, and I think it's a problem that just totally has to be solved for mobile. Rate adaptation for audio right now, we're dynamic bit rate on video. We start out low, we ramp up. But if you're on a bad network, especially in emerging market countries, even audio might be kind of dicey. And so being able to sort of scale up and down the quality on various networks, that's something we want to make sure we just nail that experience. And overall, just better performance on lossy networks. We're doing a bunch of things. VP9 has a technique called scalability built in where packets don't always have to, or frames don't always have to depend on their previous frame. So in most video compression, if you lose a frame, you're screwed, because basically any future frames will require those things that were lost to actually finish decoding. With scalability, you can basically set up a prediction structure so that some frames don't have anything depending on them. And because of that, if you lose those frames, it doesn't matter. You lose any packets of those frames, it doesn't matter. You can still keep on decoding. And so with scalability, you can actually get to a state where only 10% of the packets are really critical, or even less, to decoding the stream. And so it's the kind of thing where without adding a ton of overhead from FEC or other types of mechanisms, you can make sure that video just works magically on lossy networks. And globally, packet loss is 1%. Sometimes more, sometimes less. But lossy networks are just a thing that you always have to deal with. And scalability, I think, is a really awesome way to deal with these sort of problems. So anyway, these are the main themes going out for the rest of the year. We work on a ton of stuff. We have a decent sized team. But this is a lot of things that we want to make sure we nail. Mobile, performance, network robustness. We want to make sure you can establish calls, they get set up fast, and they stay that way. So a couple other notes from Sam. We have AppRTC, which is our reference app, and we just got a new shiny domain name for it. Thanks to our friends in, what was it, the Turkish Isles or something like that? Yes, exactly. Whatever that is. Yes. Anyway, our friends at API Days got Webrtc. So we were maybe not forward thinking enough. But anyway, AppRTC, new home. And lastly, Sam has compiled a fantastic list of resources. If you want to find out more about some of the things I talked about today, especially some of the things around signaling and how to make things faster, this is our sort of cheat sheet of all things WebRTC, g.co/WebRTC. I told Sam that mobile is important and went off and got 2 blog posts published on iOS and Android. So nice work there, Sam. Okay, so next presentation or questions, or how do we want to do this?
All right. Let's see if we got questions. Because we're broadcasting this on air as well, if we can run the microphone. Kyle, is this up? Yeah. Questions? Yeah.
My question is, I guess, I think it's awesome how much stuff that Chrome has done that enables us to do really awesome stuff with WebRTC that's kind of above and beyond the spec. And at the same time, I don't want to see that stuff slow down because it's cool to kind of push the limits. But what's the plan to kind of keep doing new stuff, but also converge at some point on the spec to have consistent APIs across browsers?
So I guess you probably mean things like promises and like some of the things where we don't currently, we deviate from the spec right now.
Exactly.
Yeah. So it's actually a funny story. We're not showing a funny story, but we've had a couple outages of the people who are actually our Blink experts. People who are actually really knew how to make the changes in the Blink, which is like the layer in Chrome, which actually implements the web APIs. We now have some new people who are taking this over, and it was really just sort of like an organizational issue. We really want to make sure we get promises. We have the output device API that's being added right now. It's the #1 thing people are asking for in terms of APIs. Promises are next. And then we want to add the sort of add track and RTP sender and receiver next. Was there anything else in particular that you wanted to make sure that Chrome caught up with?
I guess just that and figuring out all the Git stats seems to be kind of just above and beyond.
Yeah,
so.
Definitely. That's my other sort of embarrassment. I need to check and find out what exactly the status was. Somebody was working on it and there's a problem because Blink didn't support dictionaries properly or something like that. Bottom line is that the web is, even though we're focusing a lot on mobile, we still want to make sure Chrome keeps up with the spec, and some of the things where we haven't kept up, at least in the past couple months, are just purely organizational challenges. In the back. Unified plan support. Okay. So this is also one I'm going to sort of file under challenges of trying to do too much with not enough. The short answer is that we have a sort of hot list of burning features that people are dying for right now, like iOS hardware encode and that kind of thing. And unified plan support is kind of below that right now in priority. I would like to see it happen this year. So one of the things I think people here have recognized is that we kind of try to answer requests in the order that they are kind of burning, and that a certain number of requests were voted up very quickly. I noticed recently. I think somebody sort of broadcasted them on Twitter or something. But in any case, I don't think the unified plan stuff has kind of met the level of on fire must fix immediately. And so we're sort of working down the on fire must fix immediately. And hopefully, as we make some more progress and resolve some of the sort of outages that we've had, we'll be able to spend some time on that later this year.
Can you comment on how things like screen sharing are going to evolve, in your view, both within the standards and within Chrome?
Was there a specific thing you wanted to see addressed? Or
I'd like to understand whether what we have now is sufficient in your view, whether it's evolving, whether it's always going to be video, what other kinds of collaboration you see at the browser standard level versus tools that people have to build on top.
Okay, so are you referring to how the API works right now? It's kind of Chrome and Firefox have their own way of doing it? Or are you talking about what improvements might we see to screen sharing in the future? The question was about screen sharing.
Yeah, I mean, what improvements do you see coming? Where do you think it is now?
Okay. Oh yeah.
I mean,
so,
should developers, look to what's in Chrome and the standard, or should they be looking beyond that at other tool sets in order to get everything they need in terms of a more collaborative set of tools?
So let me just sort of address the question about where do we think screen sharing is right now in Chrome. And I feel like things work okay. I feel like we're supporting Hangouts, we're supporting a number of other applications, but there are definitely cases where I would not say that things are great. And one thing is people scroll, and a lot of times when scrolling happens, we see a lot of macro blocking and other sort of artifacts. And so I think there's a number of places where there's room for improvement. There's also been some people requesting the ability to share individual tabs rather than windows or the whole or the whole desktop. That's something that I think would, if enough people are kind of interested in that, that we might want to promote that higher up the priority list. Right now, I think the two things we're most interested in is sort of solving problems where we spend just to back up a little bit, we spend a ton of time solving problems where like screen share, like you change slides or screen updates, and we don't refresh the display very quickly. And the reasons for this are long and complicated. I won't get into it right now, but we spent a ton of time working on that. I think we've sort of mission accomplished on that. But still, there are cases where like scrolling or panning or other sorts of things, like we have too many artifacts. I want to fix that. That's the highest sort of priority right now. Also, VP9 has support for lossless encoding. I think that's very interesting for screen sharing. I want to sort of, once we get past some of the scrolling things, look at what VP9 can do.
What about this feature for support of changing frame rate and resolution mid-call?
Yeah, the question was, changing screen rate and resolution, you mean like sort of after the fact, like once the stream is actually hooked up, to actually then control its encoding resolution? Right, so I think this kind of gets back to the API sort of set of things. RTP sender gives you some of these knobs, and I think also like the ability to change the constraints on the track. And people ask like, well, how do I change like the resolution of a camera? Like right now you have to do another get user media to like reopen the camera at the new resolution. It's like terrible. It's like I'm embarrassed to even have to stand up here and say this. But like there's a way to do that. You can call apply constraints, and you can then change the output of the track. And that's just something that needs to be implemented on our to-do on the API list.
Maybe got time for one more, and that's it.
In the Giants hat.
Yeah, Giants hat. So what kind of performance is the WebRTC and what you just presented going to take like on mobile devices, like battery life? Because that's going to be important. I mean, how long are you going to maintain the call? How long are you going to maintain the connection?
Yes, I mean, that's a good question. The short answer is it depends. But I guess I break into three different categories. One is voice only. The second would be video with hardware accelerated video, and the third would be video with non-hardware accelerated video. And the last one is definitely the case that like you don't really want to be in. Like you'd be really looking at like talk time of like sub 2 hours or something like that. In either of the former cases, I think that it actually is quite good. The demo I just did here of like the HD stream coming off of this device was running this device at 30% CPU. So like I think I don't know exactly what that works out to in terms of talk time, but I think that you're talking about a fairly small effect on battery. For a typical 20 or 30 minute video call, a fairly nominal effect on the actual battery utilization. So that's why one of the reasons we're very excited about hardware acceleration. For voice calls, especially when the hardware echo canceller is being used, I think that it'll be very competitive with like basically a baseband voice call. And in fact, if you're doing it over Wi-Fi, it's probably actually better because running the cellular radio is like after the screen, like the #1 energy consumer. So like long answer is it depends. Short answer is for voice probably we're better. For video, if you can use hardware acceleration, you're doing as well as anything else that possibly could be done.
All right. Thank you, Justin. That was super interesting. Thanks.
Thank you all for coming out.
All right. Feroz, are you ready? He was showing me this demo earlier. It's really, really cool. So I'm really excited he's here to be able to show this.
So I invited Feroz here He doesn't want me to do an intro to, this is my pal. So a lot of talk about WebRTC is always about the audio and the video stuff. And Justin did a super job talking about all the mobile stuff, but Froze is near and dear to my heart because his focus has been on the WebRTC data channel. He's been working since we years ago. So this is some mind-bending stuff here. So Froze is definitely mind-bending. So with that,
thanks. That's better than the intro you put on Twitter for me. I think you called me the Edward Snowden of WebRTC or something. Anyway, thanks. So I heard about this meetup earlier today. So kind of speaking last minute here, but thanks for having me, and thanks to Twilio for putting this event on. So what I wanted to talk to you guys about was this project I've been working on for the last year called WebTorrent. And just kind of do a quick demo of all of the pieces that have kind of come together in the last week on it. And I think it makes for a kind of really exciting a demo. So who here's heard of WebTorrent? Raise your hand. Okay, cool. So how about half of you haven't? So I'll just do a quick actually I'll explain that later. First, I want to start off with the demo. So what I have here is a very simple whiteboard app that I built with WebRTC data channel. So you can see it's a little whiteboard. We can draw stuff. I'm not going to win any awards for my art skills here, but if you guys go to this URL on your laptop right now, you can also join me in this session. And here I actually have an Android device. This is Justin's Nexus 6 that's also here in the room, so I can kind of give this guy a body from my phone, as if the network cooperates. Is anyone else in here with me drawing? Let me refresh it in case it froze. Every time I refresh, more stuff shows up on this guy. Nice. Okay, so I'm drawing these ears here. Cool. So it's working. Anyway, so the point is, this is WebRTC data channel, right? Which is this little used part of WebRTC that most of us aren't as interested in. But I think there's actually can build with it. So this is one example, right? But we can get crazier here with this demo. So we can actually drop multimedia onto this page. So I'm gonna show you what that looks like. Here's a cat picture. What happened there? Oh, I think it's the resolution of the. Oh, geez. Okay. Let me try to fix the display here. There we go. Okay, that's better. All right. I can drop some other pictures on here. And what's going on here? What's going on is I'm actually not sending the image across the data channel to everyone who's connected, because if there were 50 peers in this room, we would be sending the data 50 times, right? And because the way this works is full mesh right now, so everyone who's looking at the whiteboard is connected to everyone else. So rather than that, I'm actually just sending across the hash of this content, and then everyone in the whiteboard room is actually getting it over WebTorrent. So WebTorrent is BitTorrent over WebRTC data channels. So to really drive this point home and show you what I mean, we can actually take the hash of the cat picture, one of these cat pictures that we added up here, and we can copy it into a little demo site I set up over here at Instant.io. And when we paste this in, the cat was actually downloaded over BitTorrent across domains. So this is using, like I said, WebTorrent, the WebTorrent protocol. So what was that? Oh, okay. Yeah. So let's see, what else do I want to show here? So I guess there's a couple interesting things here. One is that these sites are on different domains, so the same origin policy doesn't apply to data channels, which is kind of neat. I think the assumption is that if two different sites do the offer-answer exchange, the WebRTC offer-answer exchange, then they want to talk to each other, and so there's no need to do same origin, which is kind of cool. Which means that every one of you who is in this whiteboard app now is seeding these pictures to anyone who wants to download them. which is kind of cool. We can, oh yeah, the other thing I want to show is video. So let me show that before I forget. So I can actually drag videos into here. So that's pretty cool. Anyone else have their speakers up? Because then we can hear that it's actually working. There we go. Nice. And again, this works over WebTorrent, so I can actually copy the hash over, and we can see that this content is on the network. So right now, this is using a tracker server, which is centralized, and it's acting as the signaling server. But eventually, I think we could actually build a WebRTC DHT, or distributed hash table, which is actually how BitTorrent works today. And then you don't even need to have a central tracker coordinating the peers amongst themselves and introducing peers to each other. But that's something that isn't implemented yet. Okay, one last thing I want to show. One thing. So I'm really glad that Justin talked about this at I/O today. I wasn't actually at I/O, but I heard that there's some discussion about WebRTC Everywhere, or WebRTC beyond the browser. So in native apps, in desktop and mobile apps, in addition to the browser. And so I actually want to show WebTorrent working across across outside of the browser as well. So we can actually copy the same hash here, which identifies this torrent, into this terminal command here, which I have, which is a node program. We can run. It's called WebTorrent Hybrid. So this is a BitTorrent client that's command line that actually also can talk to web peers. So WebRTC is distinct from TCP UDP in that there's this offer answer exchange you have to do. You can't just arbitrarily connect to people when you know their address. It's a little bit more complicated. So if we build protocols on top of WebRTC, then what's nice is that they'll just work out of the box everywhere, in the browser and on desktop, and those apps can talk directly to each other. If you build it on any other, you build your protocol on top of any other transport, then you don't get this nice feature. So you'll see here that it works. So I'm going to pass the -- VLC flag, and that tells this program to actually stream the torrent into VLC, which is a whole another set of madness that it's kind of cool. Let's see if it's just downloading really slowly right now. This is a Creative Commons movie called Sintel, which is really kind of cool. There we go. Okay, so it's working. So here we have a browser streaming a video to VLC on my local computer. And it gets crazier. I can actually close the browser now. And if I save this hash for later, and then, oh dang, look what happened to the whiteboard while I was gone. And I go back to this page. VLC, this node program streaming stuff into VLC is currently the only seeder of this content. And now if I paste it in here in the browser, you'll see that it's actually going to send it back to the browser. So, we have like this joined network of native and web apps. And one other thing that's kind of cool is I integrated it into this open source video player called Playback, which is pretty cool. I've been using it as my main player. And so you can see that working. If I run Playback and I go to this site here and I download torrent file, I can drag it onto the player. And this native video player is going to also be able to get that video. So there we go. So yeah, all this is MIT licensed, and you should check out the project on GitHub. It's just called WebTorrent. And one other thing, if we have time for it, do we have another 5 minutes?
Yep.
Okay. So my friend John here has actually been helping me with part of this project, specifically the video streaming that you see here. Oh, one thing I got to show you this. Seeking works. So you can actually seek to a part of the video that the browser hasn't downloaded yet. Assuming, oh, you know what happened is I killed the seeder and VLC didn't get the full video, so that's not going to work. Anyway, trust me, seeking works, which is crazy. It actually reprioritizes the pieces of the video that it wants to get, and then it streams those new chunks into the video tag using this browser API called Media Source. Mostly meant for doing adaptive video streaming for sites like YouTube and just other videos. Oh, did it work? Okay, cool. Yeah. So yeah, what happened there is it reprioritized the pieces that it wanted, and then the other thing is this MP4 was not actually designed to be used with the Media Source API. So typically you have to specifically package your MP4 in a way that the video tag wants, so that you can I forget exactly the specifics, but basically, go ahead. Yeah. John will talk a little bit more about it, but anyway, it does all that in JavaScript. And on the fly. So the downloader actually repackages it so that it can be streamed, which is crazy. But John's going to show you another thing he's been working on, which I think is pretty cool. It's built on top of WebTorrent.
All right, come on. That was awesome, right? That, Chris, was why I didn't give him an intro, because there is no intro in the world that can set that kind of thing up. Come on, that's awesome.
All right, let me get set up here. All right.
Thanks. If there could be kind of entirely new categories of apps built on top of this, because if bandwidth is suddenly free for you and you can have the users of your app actually helping to host the site, I think there could be potentially new interesting types of apps that we've never thought of before. And this is actually going to be kind of an example of what that might look like.
All right, so is this on? All right, this is on. So I'm John. I worked on Pure CDN with Veras a while ago, and I've been working on some more stuff with WebTorrent. So just to continue on where Veras left off, what's a bit interesting about the video seeking is that unfortunately, when you normally use a browser with a video tag, you just put video source equals something, right? And when you do that, then the browser actually handles all of what's involved in getting the right part of the video. It does everything necessary to, get the metadata and get all the video data in the correct order. And if you seek, it'll make HTTP range requests to the server. Unfortunately, when you don't have a real source backing the video, we use this thing called media source, which is used for like MPEG dash players like YouTube. And I was also working on at Yahoo. Unfortunately, that doesn't give you any of that. So you have to repackage the MP4 file in JavaScript. And you actually have to understand the MP4 metadata, which is a bit hairy. And it still needs some work, but it's actually working remarkably well for being something I've just been working a bit on the side on. So that's not what I really came to talk to you about today. So actually just less than a week ago, I was at a conference and we were talking about decentralized systems, and I had this idea that, well, why don't we host websites on WebTorrent? So the websites themselves are distributed and they're hosted by the browsers. So let's see if it works. So what I have here is I just took a static site. Let's see here. Wrong thing. Where did it go? Oh, forget it. Anyway, so I took a static site and I just bundled it up into a torrent. And I'm using the WebTorrent seeder. So I'm going to run this. So this is actually just a demo from Angular Materials project. And what I'm going to do is I'm going to go to this browser and load this page. And you'll notice it says it's pointing to localhost. So obviously there's a server involved somewhere. But here we go. It loaded. So we have a site. We can click around. Everything pretty much works. it's fully interactive. This is just client side. So this is a site that's normally served statically. But what's interesting here is if we actually go over, this is the tab of the server, it's not even running. So how is that possible? So this was running before. I can start up the server again. And this is running on port 9100, just like you were seeing. But what's actually happening is that this tab here is creating a torrent with this info hash. And then when I go to this page, I currently just have that info hash, which is essentially a torrent identifier, hard-coded into the page. And what happens is it's fetched and presented in an iframe, just like normal. So you might ask then, how is that possible? So I have this iframe here that fills the whole page, and it's pointing at this hash /index. The way that actually works is there's this new browser API called a service worker that lets you essentially provide something that's sort of like a proxy or a cache or a server on the client side. What I can do is have my index file is really simple. All I do is just create this iframe, and the browser will make requests to this URL, and I can just intercept those requests. And all I have to do is I have a regex, and everything that matches this is fetched from the torrent. So what happens is I can refresh the site, and every time I hit refresh, it downloads it from BitTorrent. If I Control-C the feeder, on the other hand, it doesn't work. And it doesn't matter if the server is running or not. The server is only used once, and the browser will cache the actual code that does this. All the WebTorrent code gets permanently stored in the browser until you clear everything. So anyway, now what we have is, it won't load, but if I go back and restart the feeding, it'll be back. But what's most interesting isn't that. What's most interesting is if I take this, I open another tab. This could be on a different machine, of course. So this could be on hundreds of people's machines all around the world. I can load this site. Now, even if I kill the server, I can refresh either of the tabs, and it'll fetch it automatically from the other one. So the site exists permanently. If it's working, let's hope it was working earlier. I think so. Yeah, it was working earlier. Anyway, assuming it's working, there we go. It's just a little slow. I'll get working on fixing that. But anyway, you can just open as many copies of it as you want, and it'll fetch it from whoever else has it loaded. So yeah, exactly. I mean, the idea is you can make something that's, now this depends on a few centralized things. So you need someone to run this server initially, and you need someone to run the tracker. But beyond that, which hopefully I want to work on the DHT in the near future. So hopefully we can get rid of that. But the idea is anyone can run the server that's equivalent to my local host that hosts the WebTorrent code. They don't have to store any of the data. So you could make very censorship resistant sites, for example, with something like this. So if you wanted, yeah. Yeah. Right. So I mean, that was kind of the idea of Pure CDN originally, was to save on bandwidth costs. So eventually, I think what I'll do for this is make it so you can basically specify a web seed. So you can say, get it from the server if it's up, and if it's not up, it'll get it from a torrent. And then anyone can see it. Any questions? So this is just all using data channel in WebRTC to send the data. Yeah. So the service worker can do that as well. So the service worker can actually keep track of that. So if I suppose if I Service workers are essentially strictly more powerful than app cache. So they can do everything that app cache can do, but you write the code. So you can make it do whatever you want. Yes.
Sorry. Do you think it would be possible to use Git hooks to deploy to a BitTorrent? You have to have a server somewhere.
Well, I don't see why not. As long as you provide, the problem is you need to make sure something is seeding it. Otherwise, it's not going to work. So, you know, if you deploy something and then nobody can see it at all, somehow you need to, there's two things you need to do. You need to make sure it's being seeded, and you need to update the info hash. So somehow someone needs to know what this hash is. But that's essentially just a link that isn't very human readable. Yeah, so the info hash is basically a hash of the underlying torrent file, which then has hashes of each piece of the torrent. So essentially all of the assets in the entire site are bundled up into, you know, one giant block that constitutes the torrent, which is then sliced into pieces. And the whole thing is hashed. So it's basically a content addressable system. Yeah, then you have to change it. I mean, this is just something I started working on Monday. So, no, I started working on this on Monday. So it's a little bit in need of more work, let's put it that way. But I think it's gone pretty well for, you know, a few days. So I was just going to show that I can quit Chrome and restart Chrome, and the site will still be there as long as the seeder in my terminal is still up. It should load. Anyway, more questions? Yes.
I'm not too familiar with the torrent and the tracker
Mhm.
of the system, but do they handle all the NAT traversal, like assisting in NAT traversal? Or is that
So
still an issue?
at this point, this is specific to, so normal BitTorrent trackers don't. This is WebTorrent, and WebTorrent does. So WebTorrent, not really. Okay, so the actual NAT traversal is handled by a few parts. So the WebTorrent tracker does coordination that allows the peers on using WebSockets, allows the peers to agree on who's going to be talking to who. Then it uses a stun server and optionally a turn server to actually facilitate the opening of connections. Yeah, the normal stuff is all there. It just uses, yeah, it's regular WebRTC. The tracker is used, however, to, you know, negotiate the connection initially, which you need to make that work. Ideally, we could handle that with a, I don't know why that's not working, but we can handle that with a DHT, ideally. So if you have this is something I plan to work on in the future. If you have a DHT, you can do all but the very first introduction across WebSockets, or across peer connections with WebRTC. So in other words, when I first connect, then I do need to contact someone who can introduce me to another node. But once I'm introduced to one node, that node can introduce me to someone else, and that node can introduce me to someone else, until I can essentially go around and connect to everyone else in the world. Yeah. Yep. It's basically just bootstrap. Once you get it bootstrapped, then you can talk to whoever you want, as long as the network there's some path. Yeah. Oh, yeah, there's all sorts of stuff you can do.
All right. Thank you, John. I think that was amazing. You built like an entirely decentralized version of the web in 3 days, and you apologize. I go, it's a little bit slow. I'll get working on that. Yeah. All right. Justin, do you want to?
So, like, what would it take for that to be able to connect to like existing like trackers, and I can download existing torrents?
didn't have too much time to talk about this because I wanted to be quick, but the plan for that is, I mean, I don't think there'll ever be a way for like the browser to speak unless we get. I think there's like some talk of a socket API. The permissions around that sound crazy, but
It's only for Chrome extensions right now. But like,
Okay.
yeah, I mean, assume that you don't have permissions. But like, is there? What could you do?
I mean, so the current strategy is basically I want to have existing torrent clients add WebRTC.
Sounds
So-
great.
If existing clients add WebRTC, then we're in good shape. That means that they'll be able to talk to both types of peers. Actually, they already BitTorrent clients actually already support two different protocols. They do TCP and then they do UTP. So there's no reason why they can't add WebRTC and then now they can talk to browsers, right? So that and that's actually why throughout this whole project I've been trying to keep the parts that I change to the absolute minimum. So it's basically what you've seen running in the browser is basically an entire BitTorrent client, like with all the pieces, just with a couple of modifications to support WebRTC. So it should be really, really straightforward for those existing torrent clients to just be like, we can use our whole stack. We're just going to add a WebRTC transport, and then bam, now they can support this web network. So that's the plan. And obviously, I don't want to wait for those clients to do that. I think that I want to show that it can be done. So what I've done is I built that command line client you saw called WebTorrent Hybrid, which can talk to both types of peers, web and normal. And the next step is I want to, besides what you saw with Playback, that video player app that also supports it, I want to just build a standalone torrent client that I just put out there. And if some percentage of people out there start using it, then we'll have basically a nice bridge between the two worlds, the two networks. Oh yeah, and the other thing is look at Electron. Electron, have you heard of Electron? I think it's going to really help with this bridging kind of idea. Electron is used to be called Atom Shell. It's GitHub's project to help you build native apps using web technologies, and it's a lot easier than trying to build WebRTC library into your native app, I think. So if you're already using Electron for deploying your desktop apps, you already have WebRTC built into there. So that's what I'm going to do. I'm just going to, you're already running JavaScript. You just can use the WebRTC API. It's already there. It's really easy and nice to use. Yeah. I haven't looked at it since then, so I'm sure it's a lot easier. Anyway, thanks for the question.
Right. Thank you so much, guys, for coming, hanging out with us. Thank you to everyone that presented. You guys are more than welcome to stay, hang out. There's a bit more pizza at the back. There's plenty more beer. We'd love to hang out and talk with you. But thank you for coming, and thank you for coming at last minute notice. See you soon.